Section 2.6 Molecules and Molecular Compounds. Even though the atom is the smallest representative sample of an element, only the noble gas elements are normally found in nature as isolated atoms. Most matter is composed of molecules or ions. We examine molecules here and ions in Section 2.7. Molecules and chemical formulas. Several elements are found in nature in molecular form, two or more of the same type of atom bound together. For example, most of the oxygen in air consists of molecules that contain two oxygen atoms. As we saw in section 1.2, we represent this molecular oxygen by the chemical formula O2. The subscript tells us that the two oxygen atoms are present in each molecule. A molecule is made up of two atoms is called a diatomic molecule. Oxygen also exists in another molecular form known as ozone. Ozone consists of three oxygen atoms, making the chemical formula O3. Even though the normal oxygen and ozone are both composed only of oxygen atoms, they exhibit very different chemical and physical properties. For example, O2, or oxygen, is essential for life, but ozone is toxic. Oxygen is odorless, whereas ozone has a sharp, pungent smell. The elements that normally occur as diatomic molecules are hydrogen, oxygen, nitrogen, and the halogens, group 7. Except for hydrogen, these diatomic elements are clustered on the right side of the periodic table. Compounds composed of molecules contain more than one type of atom are called molecular compounds. A molecule of compound methane, for example, consists of one carbon atom and four hydrogen atoms and is therefore represented by the chemical formula CH4. Lack of a subscript on the carbon indicates that one atom of carbon per methane molecule. Several common molecules of both atoms and compounds are shown in Figure 218. Notice how the composition of each substance is given by its chemical formula. Notice also that these substances are compounds only of non-metallic elements. Most molecular substances we will encounter contain only nonmetals. Molecular and empirical formulas. Chemical formulas that indicate the actual number of atoms in a molecule are called molecular formulas. The molecular formulas in Figure 218 are molecular formulas. Chemical formulas that give only the relative number of atoms in each type of molecule are called empirical formulas. The subscripts of an empirical formula are always the smallest possible whole number ratios. The molecular formula for hydrogen peroxide, H2O2, for example, whereas its empirical formula is HO. The molecular formula for ethylene is C2H4, and its empirical formula is CH2. For many substances, the molecular formula and the empirical formula are identical, as in the case of water, H2O. Whenever we know the molecular formula of a compound, we can determine its empirical formula. The converse is not true, however. If we know the empirical formula of a substance, we cannot determine its molecular formula unless we have information. So why do chemists bother with empirical formulas? As we'll see in Chapter 3, certain common methods of analyzing substances lead to the empirical formula only. Once an empirical formula is known, additional experiments can give the information needed to convert the empirical formula to the molecular one. In addition, there are substances that do not exist as isolated molecules. For these substances, we must rely on the empirical formulas. Picturing molecules. The molecular formula of a substance summarizes the composition of the substance, but does not show how the atoms are joined together in a molecule. A structural formula shows which atoms are attached to which, as in the following examples: water, hydrogen peroxide, and methane. The atoms are represented by their chemical symbols, and lines are used to represent bands that hold the atoms together. A structural formula usually does not depict the actual geometry of the molecule, that is, the actual angles at which atoms are joined together. A structural formula can be written as a perspective drawing, however, to give some sense of three-dimensional shape. Scientists also rely on various models to help visualize molecules. Ball and stick models show atoms as spheres and bonds as sticks. These type of model has the advantage of accurately representing the angles at which some atoms are attached to one another in the molecule. Sometimes the chemical symbols of the elements are superimposed on balls, but often the atoms are identified simply by color. A space-filling model depicts the molecule would look like if the atoms were scaled up in size. These models show the relative size of atoms, but the angles in between atoms, which help define their molecular geometry, is often more difficult to see than the ball and stick models. As in ball and stick models, the identity of the atoms are indicated by color, and they may also be labeled with an element symbol.